So up until now, we have worked primarily with graphs of rectangular equations, or functions that involve two variables, x and y, specifically y being a function of x, although we have worked the other way around. So let me give a quick example of something like that. So suppose I had a projectile, and that projectile has a parabolic shape, or parabolic path. And the function to describe this parabolic path might be something like, all right, well, let's say something like y is equal to negative, let's make this negative because it would have to come back down, negative x minus 2 squared, and let's do a nice even number, plus 4, something like that. Well, if I were to graph something like this, the first thing that I would want to identify is that my vertex here is going to be 2, 4. And let's go ahead, and I went ahead and just got the graph ready for this so we can work with that. If I were to graph something like this, let's just graph that point. So if my vertex is at 2, 4, and I know that when x is equal to 4, that's 4 minus 2 is 2 squared, so that would be negative 4 plus 4, that gives me 0. And when x is equal to 0, I'm also going to get negative 4 plus 4. So you would get something, a parabola that looks something like this. Let's just draw over that there. Okay, so that would be our parabola. So this is an example of a graph of a rectangular equation, y equals negative x minus, or the quantity of x minus 2 squared plus 4. And we can see here that our y value, in this case, if that is our vertical height, if y is our vertical height, this depends on what our horizontal distance is. So y is a function of x. Y explicitly depends on what our x value is. These are what we call rectangular functions or rectangular equations. Now, today we're talking about specifically about a new type of equation, which are called parametric equations. And parametric equations are typically a set of equations that express a set of quantities as functions dependent on some other independent variable. This other variable, we will call that a parameter. So parameters are the set of independent variables that this new set of parametric equations would be dependent on. So let's go ahead and for now, don't worry about so much about how we're getting these here, but let's come up with a set of parametric equations that would be used to describe this same exact rectangular equation here. And let's go ahead and just make this a little bit smaller so that we have some space to work with. I'll just move that over here. And this one, I don't know what's going on there. Let's go ahead and move that back over there. And let's move this graph over here. So let's come up with a set of rectangular set of parametric equations. So if we say our parametric equations, and again, I'm going to give these to you right now, and in a bit we'll talk a little bit about, given a rectangular equation, how could we come up with a set of parametric equations for that, and the other way around. But for my parametric equations that I'm coming up with, you will notice that these, again, are equations that are dependent on some other variable, which we'll call a parameter. So the two that I'm giving you are x is equal to t, okay? And the other one, let's say y is equal to the quantity of negative t minus 2 squared plus 4. So what do these parametric equations represent? If we had some other independent variable, in this case t is our other independent variable, our parameter. And typically, not always, our parameter would be something like time. So what we're saying here is that x now is a function of t. X depends on what this parameter t is. Y also is a function of t. It depends on our independent variable t. So this is one way of thinking about, all right, well, if I were to look back at this original graph here, I could think about it initially as our vertical height as a function of our horizontal height. So if this projectile, like for example, like a ball that I was throwing into the air, if I could think about my vertical height as being dependent on my horizontal distance, Now I can actually track, okay, well, what is my vertical height as time elapses, right? So as time goes on, how does my vertical height change? And then that would be this equation here. Now, as time goes on, also, how could my horizontal distance change? So no longer are we thinking about my vertical height as a function of my horizontal height or horizontal distance, but actually I can think about each of those two in terms of some other parameter t. So y is a function of t, x is a function of t or time. This is my set of parametric equations. And again, I gave these to you here. So what I want to do now is for us to actually think about what would the graph of these parametric equations look like. And the graph of a set of parametric equations is something called a plane curve. It's a curve that represents two or more parametric equations. So how would I go ahead and do that? Well, let's go ahead and set that up. The first thing I really want to do is I want to set up a table. This is really going to be my first and primary thing that I'm doing whenever I'm graphing a set of parametric equations. So I'm going to set a table up with 3 columns, x and y here. And what I'm going to do is let's just go ahead and fix that. I'm going to go ahead and fill in my table for my set of t values. And usually I'm going to give you some type of interval for t. Or I might give you an interval for one of the other variables. But for now, let's just say that I tell you that t consists of all the values from 0 to 4. Let's just kind of go with that. Oops. So this is 4 and this is 0. Okay. And let's go ahead and fill that in. So when t is equal to 0, so what we're going to do now is when t is equal to 0, we are going to find its x value. Well, this is pretty easy. X is just simply whatever t is. So when t is equal to 0, my x value is equal to 0. Well, to figure out my y value, I'm going to insert or plug in t into my y equation. So when t is equal to 0 there, we just figure that out. That gives us negative 2 squared. Make that negative, and we're going to get 0 there. So pause this video right now and just fill out the rest of this table. When t is equal to 1, ask yourself, what is x, and then what is y? So if you've taken a moment to fill that out, we should get the following values. Okay, so when t, for example, is equal to 4, x is going to be exactly whatever t is, so it's also 4. And then to figure out the y, we said negative the quantity of 4 minus 2 squared plus 4, and that should give me 0. So these are our x and y values that result from us plugging in specific values for this given interval of t. Now, how do we graph that? Well, we start with our x and y values. We're going to go ahead and just plot those points here. So for us, I'm going to go ahead and use the same table that we came up with. Okay. So when x is equal to 0, y is equal to 0. So that gives me that first point there. And let's actually erase these. When x is equal to 1, y is equal to 3. When x is equal to 2, y is equal to 4. When x is equal to 3, y is equal to 3. And when x is equal to 4, y is equal to 0. And if you go ahead and connect those dots, you see that we get the same exact curve that we did initially. Okay, we get the same parabolic shape that we had before. And that makes sense because this is the set of parametric equations that represents the first rectangular equation that I presented to you guys. Now the question then is, how do I deal with this issue of t? How do I represent those t values on our graph? Well, let me change the color and kind of zoom in on that graph so we can think about specifically about those t values. So we know that when x is equal to 0 and y is equal to 0, our t value is equal to 0. So I'm going to go ahead and just say at this point, this first point where this graph starts, t is equal to 0 here. When x is equal to 1 and y is equal to 3, t is equal to 1 here. When x is equal to 2 and y is equal to 4, t is equal to 2 here. And I could go ahead and continue to label these. And you're going to see in a moment that that actually isn't absolutely necessary, but I just want you to see what the t values are as x and y change. Specifically, what you do need to do is indicate the direction that the points are moving as t increases from 0 to 4. So take a look at what's going on here. As t goes from 0 to 4, follow the parabolic path. What's happening? We see that our points are moving specifically in this direction. This is known as the direction of our plane curve. And while you don't have to necessarily label the t values, you do always need to show the direction that your plane curve is moving, because you may have a set of parametric equations that actually give you the same shape, but actually have those points changing in the opposite direction. So what we have here, these blue arrows, are our direction arrows that show the way in which our plane curve is moving. So that would be how we would go ahead and graph a plane curve. And this is the curve that represents a set of these parametric equations. These parametric equations are functions of some parameter t. And these definitions are written for you below. So what I want to do right now is take a moment and practice, one, sketching the plane curves for another set of parametric equations, and then actually practice eliminating the parameter, or actually coming up with a set of a rectangular equation from a set of parametric equations that would be given to you. Okay, so let's go ahead and try that right now. So let's start on this first problem here, where I'm asking you to sketch the plane curve that's represented here. And what's actually missing in this problem that I need to give you is an interval for t, because otherwise you could be going on infinitely. So you would want to know, okay, so for what t values am I sketching my plane curve? And let's go ahead and just do something pretty straightforward, something like -2 to 2, okay? So the first thing we want to do is we're going to want to set up a table. So again, I'm going to write my t column, my x column, and then my y column. And for t, since I'm going from -2 to 2, so let's write those in. And go ahead and take a moment now and figure out what are all my x values for any given value of t. And then what are all my y values given these values of t. So take a moment and pause and try those. Excuse me. So if you've done that, you should get the following values for x. Then you should get some values for y. And now we're ready to graph. So with these values, we start with our x and y. We're going to plot our x and y values as coordinates. So when x is equal to +7, y is equal to -4. And since we're dealing with values of all the way up to 7, let's go ahead and actually relabel our axis here. So let's actually, I'm going to go ahead and redraw my axis here. I'm going to call that my y-axis. And sorry if this gets a little bit messy, but we're just going to go ahead and 1, 2, 3, 4, 5, 6, 7. Okay. So when x is equal to 7, y is equal to -4. So -1, +1. And when x is equal to 5, y is equal to -1. At +3, I get 2. At +1, I get 5, which should be up here. And when x is equal to -1, I should get +8, which would be a bit up here. Something like that, okay? And now I'm going to go ahead and I'm just going to connect those dots. Okay. Now, so we have those x and y values taken care of. We've plotted those and we've connected them. Now we need to indicate the direction in which t is moving. In other words, did this graph start at this point? Or did it start down here? That is what's unclear to us unless we know our t values. Take a moment and pause and think about that. Well, hopefully you saw that our graph started down here at 7, -4, because that's when t was equal to -2. And up here was when t was equal to +2. So as t increases, we are moving in this direction. So here are our direction arrows to indicate the direction in which our plane curve is moving. So that's how we would sketch that plane curve. The directions asked you to check on a calculator, and I wouldn't worry too much about that, but in case you were curious, in your graphing calculator, you would want to switch your mode, hit the mode button, and you want to actually change that into PAR, which means you're going to actually be graphing in parametric equations. And then when you hit the y equals button, it'll then allow you to enter in your parametric equations, and you should see something like this. And then that's when you would write in 3 minus 2t, and then you would also want to do something like this. And you're going to want to make sure that you adjust your window. So hit the window key, or the window button, and you're going to want to change your t minimum to -2, and your t maximum, in this case, to +2. And the final thing that you want to be mindful of also is your t step. And in this case, you want to make that 0.1. So play around with that a little bit. It's not a huge deal, but if you are curious about actually how to graph parametric equations in your graphing calculator, that's how you would go ahead and do that. All right. Now let's go ahead and take a look at how we would, quote unquote, eliminate the parameter. And all this means is we are going to take a set of parametric equations and we are going to find its rectangular equation. And this may seem a little complicated initially, but it turns out it's actually really easy. All you're going to want to do is solve for t in one of the equations. It does not matter which one, but solve for t in one of the two equations. Once you're able to express t in terms of either x or y, you are going to then substitute it into the second parametric equation. And then voila, we're going to get a rectangular equation. So let's go ahead and try an example of that right now. So here, we're given two parametric equations. And again, it doesn't matter which one you choose, but we could go ahead and just solve for t in one of them. Let's just use the x one since it's the first one there. So I'm going to say x is equal to 3 minus 2t. And just using inverse operations, we're going to solve for t. So we're going to go ahead and write x minus 3 is equal to -2t. And divide everything by -2. T then is equal to, and you can write it as just x minus 3 over -2, or you can also write this as -x over 2 plus 3/2. Again, doesn't really matter because we're going to be plugging this in just a moment. So we just solved for t in one of the two parametric equations. So to come up with my rectangular equation, I'm going to take this t value and I'm going to plug it in. And let's just actually just change the color of this. And let's just make that red. And we're going to take this now and we're going to plug it into our other parametric equation. So we're going to say y is equal to 2 plus 3 times the quantity of t. And we know what t is now. T is, we can say, -x over 2 plus 3/2. Now from here, just finish solving for y. Y is equal to 2 plus 9/2, or excuse me, let's do the other part first. -3/2 x plus 9/2, and just clean that up. Y is equal to -3/2 x plus 13 over 2. And here's our rectangular equation. And you'll pause and take a moment and think about what the graph of this would look like. And you're right. It would look exactly like what we just have graphed right here above. Right? They are the same they're the same graph because this is the set of rectangular parametric equations that we have that is now written here in rectangular form. And the graph here is just a line in slope-intercept form, and its plane curve is simply that same graph now with the direction of t indicated. Now in the next part, we're going to try a little bit more practice with this.